Good afternoon, and I hope you enjoyed your lunch and your lunchtime discussions. So now we have a panel on the future of renewables, the promised land of renewable energy. How do we get there? It's moderated by David MacKay, and I'll let David introduce your panelists, if you'd like. The timing's gone a bit awry. We're going to run this panel until 3:45, and then we'll change over to the second panel in this stream. So, David.
Welcome, everyone. I'm David MacKay. I'm a professor at the University of Cambridge, and I'm Chief Scientific Advisor to the Department of Energy and Climate Change in London. And on our panel today, we have several of the Nobel Laureates you already met earlier today. And we've been joined by Elisabeth Rachlew, who leads the fusion research at KTH Sweden, and also the synchrotron research for investigation of small molecules. And from earlier, we joined again by Steve Chu, David Gross, Alan Heeger, and Hartmut Michel. Is it Michel?
Michel.
Michel, I beg your pardon. So our brief is to look at the promised land of renewables. And I don't know if the organizers chose the term promised land to give the notion of renewable energy a bit of a religious flavor, but maybe earlier today we did see a little bit of polarization of views, with some people saying, oh yes, we can do it, we can have renewables and energy efficiency, and it can all be super cheap, and maybe economists saying, no, let's be realistic, here's what's really going to happen. And the penetration of renewables by 2035, we heard this morning, will be 6 to 7% or so. So it'd be interesting to hear from the panelists whether you disagreed with that projection for 2035, and what scientific and technical breakthroughs in renewables you think are possible and credible in the next 20 years. Who would like to?
I can start.
Yes.
So since I'm leading a study of Europe to look for this for 2050, but I think in this context we are looking globally. And then for example, like we heard today, electricity is not available for a huge amount of people. And there I think that there are lots of possibilities that photovoltaic, to take care of the sun, to produce electricity, that would be a really good thing for a large part of it. And there we see many good developments, both with the materials for the solar cells and their efficiency. So the thing that is most difficult is to make it, this word you have, cost effective. So.
Yes. Maybe since the next session this afternoon is going to be addressing the needs of the developing world, perhaps it'd be interesting for this session to focus on the potential for renewable breakthroughs to deal with the developed world, and what breakthroughs there could be or need to be. And when I say breakthroughs on the science and technology side, I'd include not just the renewables systems themselves, but the support systems that the renewables might need. So, Steve, you mentioned earlier the role of storage. So, do you anticipate there being a breakthrough, say, in the cost of storage, so that batteries, say, are going to become significantly lighter and cheaper?
Well, let me begin by redefining what a breakthrough means, so that we at least are on the same page, and same page as the audience. If you consider a breakthrough in, for example, integrated circuits, a doubling of the number of transistors every 2 years, is that a breakthrough? Well, yes, I think. If it continues for several decades, it's a breakthrough. Even though it's a steady progress along certain fronts. So we've seen a similar sort of thing in renewables, in the sense that solar, it's not as quite fast. It's not a decrease in price every 2 years, but there's an experience or learning curve that's marching the price of solar, the price of wind down steadily over the coming decades. And then you say, when will it stop? Well, there you need to have a little window into the future, in the sense that where are people, what is happening in the lab? What are people trying today? And for those renewables, I don't see it bottoming out for at least a decade. So I think it still will be marching down the learning curve. And in the United States, renewables and wind, for example, as I said, in a class 3 or 4 wind site, it's the second cheapest. The cheapest is natural gas. This is the second. It's cheaper than new coal. It's about 7 to 7.5 cents of generation, levelized cost of electricity. And if you're in Europe, 7.5 cents levelized cost of electricity generation. It's cheaper than most of your electricity. That's not retail. That's generation. That's wholesale. I see a similar thing with batteries. For a long time after the invention of lithium ion, there was a stagnation. But in the last 10 years, all of a sudden, both lithium, first lithium graphite, now going to lithium silicon, the cathode materials changing, manganese mixtures, iron phosphate mixtures, all of these things. I see steady progress. I mentioned that the cost of manufacturing has dropped in half. Every battery manufacturer that I know thinks the cost will drop a half again, whether it's 5 or 8 years, somewhere around that time scale. Whether it drops to 1/4, we don't know. Now, do you consider that a breakthrough? Well, if it's slow, steady progress over a decade and drops to, let's say, 1/3, let's split the difference, that's pretty good.
Yes, so I'd personally say a 4-fold reduction sounds fantastic, though. Yes, but for storage to really achieve a breakthrough, to unlock the potential of renewables, it's got to be cheap enough that you can actually store the electricity.
So there's more depth to that. I think if you look at storage at about $150 a kilowatt hour that can store in megawatt quantities, that begins to be the utility scale stores, certainly where you can do day-night shifting. Now, do you still need something that will tide you over for several weeks if there's a several-week dearth of wind or several cloud a week? Well, there we're going to have to use, let's say, natural gas in peaking plants. But beyond things like that, this day-night shifting, $160 a kilowatt hour, even $200, but certainly $160 will do it.
So let's talk more about yes, Professor Heeger.
I personally do a lot of work. My work is focused on photovoltaics, but I'm very enthusiastic about wind, and more generally about moving turbines, whether it's wind or water. You know, there is a turbine system in the Hudson River that is generating electricity for New York. There are plans, I think maybe even partially implemented, for putting very large-scale systems into the Gulf Stream. It doesn't go off at night, and I think there are possibilities of major sources of energy from moving turbines in fluids, wind or water. It's going to be important.
So yes, some countries do have access to water that could give much more predictable power, but there are technical limits to the potential of those, perhaps, except maybe the Gulf Stream. So perhaps we should think a bit more about the intermittency side of things. So if we were to imagine a promised land in which we're using wind at very large scale and solar at very large scale. In Germany, the average intensity of sunshine in July is 10 times greater than the average intensity in January. So there's an enormous variation between seasons. So if we wanted solar to be playing a really large role, we'd need to have a way of storing energy from one season to another, not just overnight.
That's a hard problem.
Are there thoughts on that challenge and whether...
But if you think about the wind power, then there is a lot of development in the offshore wind now, so that one uses the technology from the oil companies and have mobile platforms, and you can have the stations where it's also deep water. So for example, they are building a huge wind park outside of Fukushima, which is for 1 gigawatt, and then you only need to take the cable, which is no problem then, into Fukushima, and you have the whole distribution. And for Sweden, we could have it directly if people are angry at nuclear power, you could have it outside Ringhals here or you can have it on the East Coast. It's very good, and you don't need to put all the wind inside the country. And you also have more wind and more stable, and you can also move them, so then it's even better.
But, may I object? In Germany, of course, there was lots of investment of having the offshore wind parks in the North Sea. For the moment, the tendency is going back to have more on land, because it looks like that there are many unsolved technological problems. And it looks like that it's cheaper to have the windmills on the land, despite the fact that you can produce more wind energy, more electric energy from the offshore plants.
But that, I think, is depending on the time scale you have. Of course, it's cheaper today, but they have already built big ships that bring out the plants, how to build up the offshore, and all this technology comes from the oil platforms, which is quite a nice new development. And of course, it's much cheaper to do wind today, but we said sort of 20 years from now.
Well, let's hope for the best.
It's a biofuel.
So, David, another renewable which is growing in Europe at the moment is bioenergy, that many countries are aiming to satisfy their renewable targets for 2020 by significant use of bioenergy. Do you want to
I'm certainly
comment on that?
Not an expert, but I was struck by the fact that today biofuels have barely been mentioned. I was recently at a similar meeting in Brazil, and half the talk was about biofuels, not surprisingly. And I really would like to ask the experts what is the prospects for biofuels in a way that does not disrupt the the production of food, which we also need, and destroy the water tables, et cetera, et cetera. Is there a way of taking advantage of plants?
Hartmut?
That is very difficult to use biomass. Of course, you can produce biomass, but the major point is that you have to convert that into biofuels. And this is very, you need a lot of energy first to produce the biomass, and second, you need energy for the conversion from the biomass to the biofuels. And photosynthesis as such is a very inefficient process, because there are many individual steps involved, and not all of them are perfect. They are optimized for speed, but not for efficiency. They are for individual steps in photosynthesis, and as a result of that, you barely save 1% of the sun's energy in the biomass. And you lose a lot of energy then by converting the biomass into the biofuel. And as a result of that, the efficiency for biodiesel is less than 0.1%. And you can do very simple calculations back on the envelope that when you use the entire area of Germany to produce biodiesel, you would supply maybe 10% of the current consumption of German cars and trucks. So we cannot do that. We have alternative. What is considered to be very important was that we produce maize, corn, as the Americans say, to use corn for fermentation in biogas plants. And currently, about 20% of the German agricultural land is used for maize production for biogas. If you analyze that process, you would have to double the entire area of Germany and use it completely for the growth of corn or maize, and you still would not be able to provide the current electricity from the biogas production. So that is we have already dramatic consequences, because farmers earn more by growing maize for biogas production than by growing wheat. Germany was an exporter of wheat 3 years ago. Now we are an importer. And this is simply due to the change of the usage of the land for the biogas production. And this clearly has an effect on the price for the wheat and for the food.
David?
But I think the reason I brought up Brazil was that perhaps the discussion here is a little too Eurocentric. For Brazil, Germany fits into Brazil maybe 100 times. And I was told there are areas of Brazil which are really unusable for agriculture, but great for sugarcane, and they can improve the use of the waste products that they now produce. And there's an incredible research and development area in as they already do, as you know, utilizing their natural resources, and perhaps in Africa, other places in the world. Not Germany, it makes no sense perhaps, but you know, there's the rest of the world. Is it a solution for Brazil?
That is. Of course, I ended up in a discussion with some Brazilian scientists being critical about bioethanol production, at least in Germany, because I did the calculation that you need by a factor of 400 to 600 less land for driving a car via the electric way or via the biofuel way. And they ended up with alternative discussions, but they still came up that you still need 100 times more land if you go there, even the Brazilian way. If you do the calculations for Brazil, then it's about 0.2% of the sunlight in Brazil which ends up in the bioethanol. And they don't need so much external energy to produce the bioethanol because they use the squeezed stems, the biogas, for burning. They use that for producing electricity, and they use the heat for distillation of ethanol. So this is economically more suited than it's, but still compared to the land use, it's very bad. But also in Brazil, what you observe is that you get now production of soybean in the tropical rainforest area, and the production of soybean and the yield is the lowest in biodiesel at all. Biodiesel produced from soybean, the yield is so low, it's even much lower than the production of biodiesel from German rapeseed.
Perhaps I could throw in one issue, David, if we are going for a vision of using Brazil to help out the rest of the world. 2/3 of the climate change has come from fossil fuels. Where did the other third come from? It came from mainly land use change. So people have taken land that was forested and turned it into agricultural land, and that has released carbon from the land because you get less carbon per unit area. So something to look at very carefully if we are to advocate using Brazil is the potential carbon consequences that you might be actually creating a very large carbon emission from that change of land use. I don't know if the technicians can show the map of the world that I supplied in the PDF file. Thank you. This is just to show visually what Hartmut was partly referring to. This is a map of the world showing each country's area by the size of the dot. The population density of the country is on the horizontal axis. The vertical axis is the energy consumption per person today, and they're both logarithmic scales. And that means that these straight lines of slope -1 are lines of equal power consumption per unit area. For example, Norway and Sweden and Saudi Arabia and Mexico and India back in 1990 are all consuming 0.1 watts per square meter. So that's a fairly typical figure. But 80% of the world's population lives in countries that have higher power per unit area than 0.1 watts per square meter. The UK and Germany and Japan, for example, are up at 1.25 watts per square meter. And now if you can click forward to page 6, just give it 5 clicks on the clicker. Okay, I'll do that. Brilliant. Great. I've shrunk the map down now and added some contours for the power per unit area of renewables. So when we say, oh, let's do lots of wind or let's do lots of bioenergy, this tells you what the power per unit area today of these technologies is. So energy crops deliver 0.5 watt per square meter in Europe. In Brazil, maybe you can get about 1 watt per square meter. Wind power in windy European countries delivers 2.5 watts per square meter. This is comparing primary energy consumption in these countries with so all energy, not just electricity, with what you could get from these renewables. So yes, wind power has huge potential, but you do need wind farms half the size of Germany to completely produce today's primary energy consumption of Germany. And you can put them offshore if you want, but then it'll be half the size of Germany offshore. Solar facilities in cloudy countries like the UK, Sweden, and Germany deliver about 5 watts per square meter of solar park. In sunny locations, you get about 10 watts per square meter. So there's not much of a gap between the actual consumption today of countries like Germany and the UK in power per unit area and what many of these renewables deliver. So another important issue is the actual size of the renewable facilities that would be required if we did want to have a vision of a mainly renewable future. Steve.
This is a little confusing to me because because I would have plotted slightly differently, because you need, if you're talking about renewables in terms of either biomass or solar photovoltaic, or solar thermal, I mean not solar wind, that it would really depend on how close to the equator you are. And so, for example, southern United States, Texas, Arizona, Southern California, very good places. Northern Africa, very good places for solar.
Yes. We both love data, and I can show you more data, and you get up to...
Right. And so
in Hawaii, you can get to 20 watts per square meter.
So I saw Canada and Russia up there, and I was thinking, you know, these are not good places for, you know, quite candidly, Germany's not a good place for solar. Let me also say that, you know, you can't separate land use from, there's land use for food, there's land use for energy. For most of Europe, land use for energy does not make sense. And so I think there's no disagreement here. In Brazil, let's not conflate soybean for animal feed, which is what they're chopping down the Brazilian rainforest for. It's not really for diesel fuel. It's mostly for animal feed. And so one should also mention that, that as developing countries get richer, their demand for meat goes up, and then all of a sudden you have animal feed, corn, soybean being raised for animal feed, 10 times or the inefficiency, if you will, than having people eat it directly if they want high meat diets. So this is all part of this whole thing. Most countries, biofuels doesn't make sense. I think in Brazil and parts of the United States, it might make partial sense. But in parts of Africa, again, not to chop down rainforests, but there are parts of Africa that do make sense. But most of the other places around the world, Europe especially, there are also parts of Asia that don't make sense for biofuels. So it's not as simple as a yes or no.
Yes, that's agreed. So attention often focuses on electricity, but there are these difficult to electrify sectors, the transport side of things, especially freight and international shipping and aviation, and there's the whole of industry. What do you think is the best way to, if renewables are going to penetrate those difficult sectors, the transport and the heating and the industry, how do you think that would be delivered?
Well,
David.
Biofuels would seem to me to be, perhaps developed particularly to have a replacement for fossil fuel airplanes.
They exist, yes?
Yes, you can.
For what for? Yeah. Well, if first let's start with airplanes and long distance travel. Airplanes, trains where there's no electrification, and boats. Then we're mostly talking about liquid fuel, high density, especially airplanes. And in that case, it could be biofuels, it could be it's going to be a liquid hydrocarbon. If you have inexpensive electricity, really inexpensive electricity, you can maybe use the electricity to form a liquid hydrocarbon. The verdict's not in. Right now, what we do know is that biofuel, jet fuel replacement is not competitive with petroleum. In fact, nothing is competitive with petroleum currently. But this is a science issue as to whether we can actually invent something.
Elisabeth?
Yeah, I wanted to say we had a study here in Sweden, and then about the biofuels, and then we really came up with that we should go to methanol. That would really be the way to go. And as I understand, they have many cars in China already run on methanol. In Sweden, it's not allowed to have methanol in the cars. I don't know why, but that would really be, and we could produce methanol also, right? So that would
possibly for cars, but but not for airplanes.
No, but for ships. For ships, there are big ships company going now.
Ships possibly, yes, but not for airplanes.
Not for airplanes, no.
Many people who have a vision of a promised land of renewables actually have different visions from each other. For some people, it's about localism and community ownership and decentralization, and for others, it's about going and invading Brazil. Sorry, not invading Brazil, but asking Brazil politely if David can go ahead and do lots of bioenergy in Brazil. And international supergrids and tankers taking bioethanol from one place to another. What's your vision? Maybe I could go through all of you and ask, in that spectrum, what you think the promised land would be like. David?
No, I'm a little confused as to what you're getting at. At some point, we will run out of petroleum. We all would like to come to conferences like this. We will require airplanes and some high-density fuel. The only one that exists now is petroleum or biofuels. We'll have a lot of useless tankers, by the way. So the distribution problem isn't necessarily the problem. We do that now with fossil fuels. And we probably should try to think of I mean, this is actually a great place where a scientific breakthrough could make a difference. There's very little incentive to invent a replacement for airplane fuels now. It's available and will be perhaps for a century or two.
So I was asking a more general question than just aviation.
And as far as your panoply of possibilities, obviously one should do all of the above. I mean, there are local solutions and there are global solutions, and it's not either or, but both.
And again, it depends where.
Yeah.
In a city, putting it on the rooftop, putting it on the facade of a building, local. My house is the right way to do it.
In some countries.
That's what I say. But other places, power plants with, solar farms, so to speak, is the way to do it.
I also would say that it's the best to produce as much energy locally as you can. And if you look for the photovoltaic cells, it makes much sense that each roof is covered by photovoltaic cells, and the local owner or the inhabitants of the house use that electricity. In Germany, we pay to our power supplier 30 cents per kilowatt hour. And this is actually, if we produce it with the current technology from the photovoltaic cells ourselves, it's cheaper, we save money. So that's a clear advantage. And the other thing is storage of electric energy. At the end, if we have much better and safer batteries, each house should have a room somewhere in the basement where we can store the energy which is consumed by the people of the house for several weeks. So decentralization is a major thing. But globally, a major breakthrough, I would think, would be to have high-temperature superconductivity cables. This would mean that you could transport electricity without a loss around the globe. And if it's always light is shining on 2/3 of the globe. So you can have the energy from there and transport it without any loss to the places where you need it in the night. So high temperature superconductivity would it be, in my opinion. But this is, of course, we have to find out how to get that, and we have to understand high temperature superconductivity. That's a problem for physicists and material scientists and so on, but this, in my opinion, would be the ultimate solution.
So the international supergrid has one advocate.
That would be a breakthrough.
High temperature superconductivity would be a breakthrough that would help us on many different things.
And it's also very difficult.
Shall we go to the audience for some questions? Please put up your hand if you'd like to ask a question, and we'll get a microphone to you. Yes, up there, halfway up, a second in. Thank you.
Hello, everybody. I have a question regarding the fact that you previously said that it's not thinkable or likely to use biofuel within airplanes or planes. Would it be possible to perhaps use the same technology as in some submarines with nuclear power?
So let's first, you must have misheard it. We did not say that biofuels cannot be used in airplanes. What was said was that currently biofuels for jet fuel is not economically competitive. Okay? You can actually make jet fuel but from biofuels. There have been E. coli and yeast that have been reprogrammed. You feed them simple sugars, they will make replacement jet fuel. But it's the commerciality, the feasibility is the question.
I think Richard Feynman had a story about the patent people coming to see him when he was working in America, and they wanted him to make more patents, and he said, "Oh well, you want patent ideas? They're easy to make." And one of his ideas was the nuclear-powered airplane, and his story ended up with he gave them a list of things that he invented, and apparently they did patent one of his nuclear-powered something or others.
But also, in regard to your question about, you said essentially I was hearing nuclear-powered airplane.
Yes.
Was that the suggestion or question?
Yeah.
Well, its crashworthiness would be of some concern. And it's too heavy. The shielding is a non-starter because of the.
Wouldn't work either.
Yes. There's a lot of things that would not make it feasible.
Let's take a question from the internet, please.
Yes, thank you for the interesting discussion so far. We have one question from the online audience. What do you think is most important to speed up the development of renewables and drive down the costs? And what do you think is the largest hurdle? I mean, solar and wind are becoming competitive, but what about other renewable technologies?
Let's make solar and wind first. Let's get it there. We know that the capability is there. The efficiencies are going up, the costs are coming down. Now we have to implement it.
So what's the best way to drive down costs? Is it to give money to researchers and the inventors in sheds who are coming up with new prototypes, or is it to have government-led subsidies pulling through?
Well, giving it to research is, as we've heard, slowly returning. Time scale is long. It will work, but it takes time.
Elisabeth.
But you also have to have the effort between the scientists and actually making the prototype. With my colleagues who are working on the photovoltaics, and they have got very good results, but then the money must be there to start the sort of bigger test plant also, and that is where one should put in some effort also now.
You can make pilot line scale, which is a good way to test, of course.
Steve, I'd love to hear your answer. You must have had a big budget, and you must have thought about the trade-off between investment at various stages of the innovation chain.
Well, while this was going on, I was actually thinking about the nuclear. So let me just finish this. There is one caveat on what I said, and that is nuclear as a thermal source has been used in satellites for many decades. So it's not the standard type of nuclear reaction you have in nuclear reactors, but it's nuclear where it's alpha emitters, it's easily shielded, but there's a power issue. It's not high power. But you can take these things, you can put them on a satellite, and you can send them to the things that were powering the satellites that go flyby to Saturn, to Jupiter, Uranus, and Voyagers. These are nuclear powered, but of a very different type. So just to complete the answer to that, I didn't want to give saying that nuclear power is not, it's still not practical for airplanes.
And in the good old 60s, I think the Americans did put a reactor on an airplane. It wasn't powering the airplane, but they did show that they could have a reactor in flight, and they managed to shield the occupants.
Yes.
But Steve, I'd really like to hear your answer to the question we just had, which is, what's the best way to drive down the costs of renewables? So you've seen the world from the lab end, and you've been in the Department of Energy.
Yes.
What's the right way for a government to drive down the costs?
I personally think the best resources for the government is mostly in the research and development. The more it gets towards demonstration, piloting, and deployment, the less the government should be involved in it. First, it's too costly. Secondly, it should be ripe for the private sector to be picking it up. I'm not a big advocate for spending many billions of dollars to nudge something forward, because I've seen too many times where you invest $1 billion or $500 million or $2 billion in developing a technology, and then the only reason the private sector is partnering with you is for that subsidy, their business plans, when the subsidy goes away, they go away. And so I'd rather, and that's why I talked a lot about driving the costs of solar down, driving the cost of wind down, driving transmission distribution. Long before we're going to get superconducting, what we in the Department of Energy decided that if we can improve the electronics that allow you to step up voltages to make it high voltage DC and step it down very efficiently, that's pretty good. China has a 800, plus or minus 800 kilovolt DC line. It's about 1,000 miles. They lose something like 5 or 6% of the energy, power. That's pretty good. And they're building a 1 megawatt volt line. Okay, that electronics, that's within our grasp. That's the kind of technology we would need to put solar panels in the Algerian desert, okay, in Libyan desert. You don't need, 1,500 miles is good enough for a lot of things.
So Steve is favoring innovation support and implicitly criticizing the more European approach, where we also have extremely large, tens of billions per year being put into subsidies through feed-in tariffs and so on.
They must have a gradual sunset. German tariff actually did have a sunset. It was a little rich for my taste at the beginning, but you still need a sunset clause. I think wind, by the end of this decade, in the United States at least, even the Wind Association says we don't need a subsidy.
And do you think it was a mistake along the way to give so many tens of billions to these technologies through feed-in tariffs?
No. I think in the beginning, renewable portfolios and something like that was important. But right now, wind and solar are at a very different place. And so 15 years ago, 10 years ago, 20 years ago, perhaps so. But we're getting in a comfortable place.
Would anyone like to add in before we go for the next question?
There's one other topic we haven't discussed much. Maybe it's because it will be discussed later, which is nuclear power, which I think is something that scientists, especially physicists, can speak to because it's taken sort of for granted in many places throughout the world, especially in Europe, and that this is not a part of the solution, and I simply cannot understand that, except for irrational reasons. And it's, us scientists should combat that irrationality, I think.
Yes, when we were given the title of this session, it was about renewables, but I did wonder whether we were allowed to talk about the promised land of low-carbon energy and generalize it.
Nuclear power and eventually fusion power, which we assume will work on the timescale that we're concerned about, are pretty renewable by human scale. And
yes.
And like with the issue of climate control, the debate and government policy is more governed by irrationality than by rationality.
Who'd like to respond? Elisabeth, you work in fusion.
Yeah, since I work with fusion, but now I work a lot with fission also to look at it, and saying that nuclear energy is not something where everything is put in a box and fixed, and either you have it or you don't have it. It's a field where you develop a lot. And if you think about the fission there, we have generation 2 and 3, and now we have water cooled. We can go over to have liquid metal cooled. There have already been reactors working like that, which have been closed down. We can have a closed fuel cycle. We can use thorium as the fuel also. So we have now quite a lot of fuel that we could use again in reactors, so that we don't need even to take up more uranium. We can have a combination of fusion and fission. Our old jet constructor, Professor Reby, he thinks so now, that would be faster to go through than a fusion reactor. And with the fusion, we really have a fast track already for saying where we go. Right now, we are building ITER, which is the worldwide experiment with 7 parties. That will start in something 2018-19, and maybe by 2030 we will be ready to say what kind of fusion reactor should we have as a demo. So it is a little bit longer time scale than you had here, but it's definitely one of the base powers which is fossil free. So I think also, like David Gross said, you said it very well, that it's really irrationality, but then we need to meet that. So we need to meet it through education.
Hartmut, you live in Frankfurt, so you're in a country that David was referring to a moment ago. What's your feeling on this?
About nuclear power?
On nuclear power, yeah.
Nuclear power, I think it was a wrong decision to switch off the all the nuclear power, to make the decision to switch off the nuclear reactor so early. This was simply because the German Chancellor wanted to be re-elected. That was the only reason, in my opinion.
Let's go to the audience for another question. There's someone in the middle there, 2 in. 5 rows back, 2nd in. Where's my second microphone?
Hi, my name is Chuck Cornell from the University of Nevada. I want to thank you very much for the very interesting conversation. I've been intrigued by the conversation of renewables, and especially the lack of discussion about geothermal. In my hometown in Reno, Nevada, we have about 40% of our power is produced by geothermal, and I understand there's important geological reasons for that, but enhanced geothermal is something that perhaps should have some future, and I'd be curious to hear your comments about that.
Good. So the question's about enhanced geothermal, where you drill down up to 10 kilometers deep, crack the rocks, pump down water, and get very high temperature steam coming up the other side. Who'd like to?
Iceland.
Yeah. Yes, so Iceland is a prime example. Steve?
Well, I think he's talking about, Iceland has natural geothermal, meaning that it has the water supply. Nevada has the geysers and other places. They have natural geothermal in that there's a basin, there's a natural supply of water. So what he's talking about is enhanced geothermal, where you actually supply the water. You then extract the heat from the water, and then you try to recycle the water back as much as possible. It can also be generalized not only to water, but to carbon dioxide. Carbon dioxide has less heat capacity, but it has lower viscosity. It has maybe its density might be 0.6 relative to water at those temperatures and pressures. So one of the issues is induced seismicity in geothermal. One has to do these experiments for some reasons, unbeknownst to Californians. Magnitude 3s get people nervous, but a magnitude 4.5 would stop everything in its tracks. And so induced seismicity is a problem. The other thing about enhanced geothermal that one has to realize is, except for those rare natural cases which seem to go steady state, if you look at, for example, the MIT report on enhanced geothermal, it's a heat extraction for a couple of decades, and then you've kind of done in that reservoir, and you have to go somewhere else. It's not a forever heat extraction. The conductivity of the rock is too slow. And so then you have to go somewhere else. You can maybe return decades later.
Centuries later.
But that becomes more expensive because of the piping. Also, drilling technology has to be improved. When you're drilling for oil at $80 or $100 a barrel, that's okay. When you're drilling for heat and you're going down as deep, that gets a little dicey. So, but the good news is that drilling technologies can also improve, especially if you can start to drill with seamless pipe, drawn pipe, rather than steel pipe that you have to screw together. Now, that's a drilling technology. That means you need a totally different type of bit. The way we drill today is we have weight on bit. So this is the Howard Hughes diamond patent drilling bit that hasn't really changed that much. There's a new technology where you have laser ablation assisted grinding. The weight on bit becomes drastically less. The amount of power going down several kilometers is still possible in multi-mode. If that's the case, then you can be having tubes on long cabled tubes. Then you're in a new ball game. Then geothermal may become possible. But this is research. I happen to know this because we sponsor this research, we, the Department of Energy. But that could be a game changer if you can get drilling without weight on bit. If you can get drilling that has seamless tubing instead of screwing pipes together, then you're in a totally different ballgame. But that would also be good for geothermal locally, for homes in the Midwest in the United States. You go 30, 40 feet down, it's about 20 degrees centigrade. That's, you know, Goldilocks just right. So in the summer it's too hot, in the winter it's too cold, but you just have a very modest heat exchanger, and it works great.
Alan, Elisabeth and Alan.
Yeah, I can just add that in Sweden they're building quite a lot of drilling about 100 meters down, and especially for single houses. But now they have allowed even in Stockholm to drill in the pavements where we are walking. So now they drill a lot. And there was even a couple of years ago, the drill came down just in front of the subway, because things go so quickly now that they haven't coordinated all the approvals departments in the city.
Your energy is higher than our energy. A lot of things you do in Sweden we can't do in the United States. You're 2 or 3 times higher.
Okay.
I wanted to finish with a question of mine, which I sent to you before. It's a question about memorable scientific facts or numbers that you think everyone ought to know. I was wondering, do you have a favorite important fact or number that people should know to have insightful, constructive discussions about energy options? David?
Well, my only suggestion is look it up in your book.
Oh, thank you. That's very kind. Elisabeth?
Yeah, I have the same answer. What is it, about 100 watts per square meter?
For those of you who don't know, what they're talking about is a sort of incident energy on Earth. There's another one in addition to that. The incident energy is embedded in the equatorial plane, which really cries for transmission and distribution. The other thing is energy density per unit weight and energy density per unit volume, as well as energy density of sunlight hitting the Earth.
Yeah. Alan? Hartmut.
So many kilowatts per square meter, and 1 kilowatt per square meter at noon in Santa Barbara?
Yes.
Important number.
Really? I would say it's that if you produce biofuels, you store less than 0.1% of the sun's energy.
Using plants.
Using plants.
Using plants.
And algae.
Well, I'd like us all to thank our wonderful panel for a very interesting discussion. Thank you very much.